In this video, I'm going to talk a bit about the idea of a wave function. Right, it's a tricky topic to introduce. Basically, a wave function is just a function that describes the wave. So, for example, in this wave that you saw in the last video, where I described this wave that goes up and down and then eventually goes to zero. This very shape, if you imagine a function for this graph, then this is a wave function. And I've drawn other types of waves in the previous videos, and all those different wave shapes that I've drawn, you can think of them as just wave functions, or which are basically essentially graphs of the waves. And this requirement that I described in the last video about energy conservation and about how momentum has to be related to the wavelength by the Broglie's relation. Based on these ideas, equations, rather complex equations, has been developed that makes it possible to calculate the actual shapes of the waves or of the wave functions. Now, I shan't go into those details of the very deep and difficult mathematics here. I'll just say that I'll just look at some examples of the kind of wave functions we might see. Okay. Now, since we are here, we are looking at this atom right now. Let me just maybe tie up a loose end about Bohr's model of the atom. So if you recall, in Bohr's model of the hydrogen atom, okay, there is a positive proton. There's a proton at the center of the atom, and there is around the atom an electron orbiting the atom. And we were saying that from the understanding of the Broglie's relation, one of Bohr's condition for the hydrogen atom, for the orbit, is basically a wave going around the atom that has to close back on itself. In other words, around the circumference of the orbit, there must be a whole number of wavelengths, right? A whole number of wavelengths must be equal to 2 pi r, the circumference of the orbit. And this forces r to take only certain definite value. Now, but if we carry this idea over now to what we understand of waves, we have a problem. Now, if you think about what happens, if you imagine plotting a graph of the wave along the radial direction, that means not around the orbit itself, where obviously we can see a whole number of waves, but imagine going out from the center, from the nucleus outwards. Now, if you imagine plotting a graph of that, what would it look like? Well, if we take this idea seriously, that r can only take certain definite values because of the requirement of whole number of wavelengths around the orbit, it means that just below this radius and just above this radius, there must be no electron. So if I imagine plotting a graph of the, say, maybe about the electron, about whether I can find electron, then what I would expect to see is that I can't find electron below the radius of this orbit, but at the orbit I can find the electron there. I have a big amplitude of finding the electron, and beyond that orbit I can't find the electron there. And maybe until the next orbit, then I might have a chance of finding an electron there. But on either side of it, or of the orbit, there's no chance of finding the electron there, simply because according to Bohr's model, the electron must be in at only certain radius. But that gives us an immediate problem, because it means that if you look outwards away along the radial direction, it looks like we have a very sharp wave. We have a very sharp wave. And as I've mentioned previously in the last video, if a very sharp cut off the wave or a very sharp change in the wave, it's like a wave which is oscillating very rapidly. Okay, so it's like a wave with extremely short wavelength, right? Because if you imagine very rapidly oscillating wave, then one of the peaks would just be a very sharp thing like this. So it means that this suggests that the wave has the electron has a very big energy or very short wavelength down here. That can't be right, because we have calculated the energy previously, and it is not like an infinite amount of energy. So what this means is that even along the radial direction, we should expect a wavelength that is not so different from the wavelength around the orbit. Okay, because the particular electron just has a particular energy, whichever direction you're talking about. So it means that we would expect, therefore, that along the radial direction there must be a wave that perhaps looks something like this. And from what we understand from the last video, as you go further and further away, if the electron is actually able to move outwards, rather than just going around the orbit, then at some point it must have used up all its kinetic energy against the attraction from the nucleus. So at some point, the wave must fall to zero and stay there, stay at zero. Right? It can't keep being a wave forever, since that would mean that it can actually appear very far away. The electron can actually be very far away from the atom. The electron must just stay around the atom. So this means that we would expect to have a wave both, in the orbits round and round the atom, and also in the radial direction. So in other words, we expect a three-dimensional wave. So this means that we can describe this three-dimensional wave by a wave function. Let me write down this word, a wave function, which is essentially a function which is usually denoted by this letter psi. So this is a Greek letter, it's pronounced psi, psi, and it's basically just a function of x, y, and z, of this space, this three-dimensional space, x, y, z. Okay, now, but this wave function, it doesn't have to be something abstract, right? In this case, it looks a little bit abstract because we are thinking of it in three dimension. But if we just think about an example which I've used quite a bit when I talked about the uncertainty principle, I have often, and the Broglie relation, I've often just used a simple sine wave that goes on forever. Okay, so that would be like sine kx. So this would be just like a sine function, sine of some number times x. Okay, So, and this is just in one dimension. If I just think about a wave going along the x direction, so I can think that this function is the wave function as well. So just a simplified sine function in one dimension. So psi of just x, just one variable instead of x, y, z. Okay, so this is a lot simpler. Just psi of x, a function of x, and it's just a sine function, just our familiar sine function. So that can be a wave function as well. So this sort of represents a particle that has a fixed momentum, p equals to mv, meaning going at a constant velocity, and we know from the Broglie's relation that the momentum is equal to is related to the wavelength by h over p. Okay, so where this is the wavelength. So that's the wave function. And the other example which I have used when I talked about the uncertainty relation was what happens when if we add up a number of these sine functions with different wavelengths. And we've seen not too many videos ago that we would get a wave that looks like this, that has a bigger amplitude near the center and sort of amplitude gets smaller and smaller as it goes further out. And that's supposed to and we can understand this, right? We can understand this as a wave in which the particle is kind of around here, around the region of the wave where there is obviously peaks or amplitudes, and further away where there's very little wave, we would expect that we can't find any particles there. It's more likely that the particles would be around here. So I've been using this description that it's more likely to find a particle where there is the wave, and obviously the wave has to do with the amplitude, because if there's no amplitude, there's no wave. So in this way, it kind of leads on to the idea of a wave function, where if we try to write down a precise mathematical formula for the wave function like sine kx, then this wave function now has a value. Okay, this wave has a value, has a formula, and it must somehow be possible to relate the probability, the likelihood of finding a particle at a certain position x. That probability must somehow be related to the formula for the wave function. So how exactly is it related? I write down the relation here. Psi of x, okay, let's say I have a function psi of x, which can be, say, sine x, or it can be something more complex like this pulse here, or it can be something even more complex like this three-dimensional wave. Right, this wave sort of goes out in all directions and round. Function of x, y, z, or three-dimensional space can be more complex like that. But whatever it is, if there's a wave function, the idea is that if we take the modulus of this wave function, meaning okay, the meaning here is a bit subtle, but for now let me just assume that this is a real number, so it can either be plus or minus. So if I take the modulus, it means that if there's a minus sign, I just drop the minus sign, take the positive value. So if I take the modulus and square it, the answer must be equal to the probability of finding the particle In this case, maybe say the electron, but it can in general apply to any types of particles like protons, neutrons, and so on. Probability of finding the particle at the position x. So this is how it is often described. Now it's a bit not obvious why we need to square it, and why we need to square it. Amplitude may be understandable, because even if I have a negative peak or trough down here, it means that there is wave there and I must have a chance of finding the particle there. But square, why do you have to square it? Okay. Now, I won't be able to go into the details of why you have to square it, but I'll just say that it has been found that if we square it and we use the result to do calculations about atoms, about light emission, about chemical reactions, and about bondings, and so on and so on and so on, people have found that the results agree well with observations and experimental measurements. So it's something that has been checked and verified over many years. So today we accept that, at least for practical purposes, if we can find a wave function, right, either using this the complex equation for the 3D, or when we think of simple ideas like the uncertainty principle, constant velocity, the Brule's relation, or a pulse like this, whatever it is, if we just take the modulus squared, that gives us a probability of finding the particle at x. Now, but at this point, let me just mention one subtlety about this function, which is that the probability of finding a particle at x, if this is a continuous function like this or like this, okay, now the probability of finding the particle at a particular point, to be very precise, is actually 0. Simply because if I have a continuous wave like this, we would expect that this probability is distributed continuously over a certain region of space or over a certain range of x. So that means that that actually means that in order to find the probability, it only makes sense to talk about finding the probability over a certain range of x. So for example, if I actually square this, I might end up with a graph that looks like this, where all the negative values become positive. So if I want to find, say, the probability that x is between A and B, okay, the proper way to do it is to, let's say this graph is the graph for this psi squared. The proper way to find the probability that an electron is between A and B is to find the total area under the graph between A and B. Okay, that's the proper way to do it. But in any case, it is often just loosely, this modulus squared of the wave function is often just loosely described as the probability of finding the particle at x. And by that, we might imagine that it could mean, say, it might just mean the probability of finding the particle at a very small volume around x.